Hello, everyone. Welcome to another class. At this time, we'll be taking Radioactivity Part 2, and I hope that you pay rapt attention as we dive into the class. I'm going to share my screen now, and we're going to get straight into it. Radioactivity Part 2. In this particular one, I'm going to deal with artificial transformation. Let me start from the terminology artificial transformation. And this concept of artificial transformation, let me talk about it by saying artificial transformation is induced in an element by irradiation, exposure to radiation. That's the meaning of irradiation. So artificial transformation is induced in an element by exposure to radiation, either by accident or by intent. So you discover that if we go back in, for some of you that watch some series, remember that it was particle acceleration, the occurrence of particle acceleration that created the idea of the Flash and some other, heroes and villains in that particular series. So we see that what happened there was artificial transformation. When particles hit those people, radiation, and in that particular series, you see that the idea was accident. There was an explosion and there was particle acceleration and all of that. And it created new beings, new people, some were villains, some were heroes. Now, I'm just using that analogy to tell you that artificial transformation is induced in an element by irradiation. Irradiation is the exposure to radiation either by accident or deliberately. So get that idea. It was first achieved by Rutherford. An ordinary material not normally radioactive is made radioactive by bombarding it with radioactive particles. And an example that we have here is we see 4,2 helium plus 27 aluminum giving us 30, 15 phosphorus plus a neuron. So an ordinary material, not normally radioactive, is made radioactive by bombarding it with radioactive particles. So that's the idea. So just like what we see here, you bombard it. Here, the radioactive particle is alpha particle. We bombard it with aluminum, and we create, a radioactive particle. Yeah, phosphorus. So that's it. So we create a radioactive one by bombarding it with radioactive particle. Yeah, the radioactive particle is alpha particle. Now let me go quickly to talk about something else, nuclear energy. The protons and neutrons in the nucleus of each atom are held together by very powerful nuclear forces. Let's continue talking about this. An enormous amount of energy is required here the nucleon apart. So we can define nuclear energy nuclear energy can be defined as the amount of energy required to hold together or tear apart nucleon. So that's nucleons means protons and neutrons. And let's continue. Enrico Fermi in 1934 discovered that the nucleus can be split by bombarding it with a slow neutron. So that was his discovery. And how do we do that? We write that equation like this: neutron plus using uranium as sample. When you bombard it with a slow neutron, it splits into 141 barium So let me shift this to the side to make sure I have space to do what I want to write. So it split. We split this particular one into three things: 1, 2, 3, and we get energy. So you split it, can be split by bombarding it with slow neutron. So you see that is the energy required. So the energy that is released there is nuclear energy. So that energy. So let me Let me diagrammatically express this. Just like a neutron is coming and it hits a particular element, and then what we see, or let me see, let me do it the way. It's coming, hits this, and then what happens is the energy required to pull them apart now pulls it apart into two, and then releases 3 neutrons. So you see 3 neutrons here. You see this one can be 9 to 36. Let me see, this was uranium. We have Kr here, we have barium here, and this is the energy. Let me put it like a blast. And let me do it like a, let me draw something more like the flash. So this is energy, this is barium, this is Kr, and we have neutrons. That's like, this one is N. So that's the idea. 3 of them are released. So just by bombarding, this was also bombarding a slow neutron with uranium. You see the release of barium. And then another element, I'm coming. And then 3 neutrons. So that's the idea. He discovered, at this Fermi now, he discovered that the total mass of the component products is less than the mass of the original materials. So what we're saying here is that he discovered that, oh, when these things were released, when this side, what we have on this side, when we calculate the mass, I will compare it to what we have on this other side. They discovered that this one here is less. This one here is more. So he now said, okay, the difference in mass, which we call mass defect, is a measure of the nuclear energy released. So he said we can find that difference in mass by considering an energy that Albert Einstein defined as. So Albert, let me do it like this. According to Albert Einstein, one of the world's greatest brains, Albert Einstein, E equal to mc squared. Now this change in m here is the mass defect. So let me just erase that. Hold on. So let me write that again. So change in m is mass defect. E itself is nuclear energy. The C that you see there is the velocity of light. That is a constant. We talk about nuclear fission. Nuclear fission, this is the splitting up of the nucleus of a heavy element into two approximate equal parts with the release of a huge amount of energy and neutrons. So in fission, we see splitting up to release huge energy and neutrons. So, for example, if you go back to the example above, that's an example of fission. So that this one that we have above, I can copy it. Make sure that I'm copying it well. Copy. And I've pasted it here. So you can have that, excuse me, can have that as an example of what? Of fission. So that's the idea. You have that as an example of fission, nuclear fission. Why? Because you have uranium right here. It splits up into two. So splits up into two, these two guys, and also we have neutron and energy. So that's how it works. So let's continue by explaining that these neutrons, no, let me make a statement before that. Fission occurs with most of the massive nuclei. When the heavy nucleus is bombarded by slow neutron, several neutrons are produced as byproducts. So the idea here is that fission occurs with very heavy nucleus, and then that nucleus is bombarded with a slow neutron, and then it produces several neutrons. For example, in the above case, it produces three neutrons as byproduct. Now, these neutrons may cause the splitting of other nuclei which in turn yield more neutrons which may further which in turn yield more neutrons, which may further split other nuclei and so on. So the idea here is that once those neutrons are produced now, they can also combine with some other nuclei and cause fission to occur again. And when such thing happen, let me explain the idea I'm saying. You have a neutron bombards with a nuclei and produces smaller nuclei, and produces other, like about 3 neutrons, and then those neutrons combine with some other heavy nuclei and produce smaller nuclei and produce some more, and those ones combine again, and it goes on and on. And the same thing happens here. So we see, so it goes. So when you have stuff like this, the idea is that those neutrons combine with heavy nuclei, they keep combining. So if you have something like this, you can call this a chain reaction. What do we say? A chain reaction is a multiplying and self-maintaining reaction. A chain reaction is a multiplying and self-maintaining reaction. When the size of the nuclei exceeds a certain critical mass, there is a rapid production of neutron accompanied by a release of tremendous amount of energy in a nuclear explosion. This is the principle of the atomic and nuclear fission bombs. So the idea here is that whatever is used in the present day nuclear bombs is a rapid production of neutrons accompanied by a release of tremendous amount of energy. That's what gives nuclear explosion. So let's now go to fusion, nuclear fusion. This is a nuclear process in which two or more light nuclei combine or fuse to form a heavier nucleus. With the release of a large amount of energy. So two or more light nuclei combine or fuse to form heavier nuclei. The release of large amount of energy. So we see, for example, let's see the light nuclei 2,1 hydrogen plus 3,1 hydrogen, giving us 4,2 helium. And then we have neutron and energy. So in this case, there is fusion. These two things fuse to form one thing. Two fuse to form one. And then neutron and energy. So this is neutron and then energy. So let me do it this way. Here we have deuterium. This guy is called deuterium. Combines with tritium. These are isotopes of hydrogen. That is, normal hydrogen is 1,1. But because this particular isotope, this one, has one extra neutron, it becomes 2,1. Then this one has two extra neutrons, and that's 3,1. So that's the idea. Tritium and deuterium, the isotopes of hydrogen, they combine to give helium. And then neutron and energy. So the idea here is, if I draw it diagrammatically now, this guy has a proton and a neutron. Deuterium has a proton and a neutron. White tritium has two protons, two neutrons and one proton. When they come together, it gives us two protons, and we have three protons. But those three protons now, they now split into, we now have a result of two of them come together with two of the protons, and then we're left with one more neutron. So here we have two neutrons, two protons, one more neutron left, and then energy. So that's what we're seeing right here. These two things fuse, and then they give us the result of helium, neutron, and energy. And then we can say to bring the two light nuclei together in a fusion process, very high temperature. of the order 10,600 degrees Celsius are required to overcome Coulombic, or let's say Coulomb repulsive forces. Now, why are we talking about repulsive forces? We know that when we are trying to bring these two together, since we have positive charge here and positive charge here, they are supposed to repel. They are supposed to repel. But since we are dealing with high heat, very high temperature, that particular repulsive force will not work here because the temperature is going to break it. It's going to break it so that fusion can occur. So in fusion, we require very high temperature to overcome, to break the repulsive forces between the two nuclei. We've established that the atom is neutral, but the nucleus is positively charged. Why is the atom, in previous classes, we established that the atom is neutral because there is an electron in the orbit, which is negative. And in the nucleus, we have proton and neutron. But that proton and neutron one is positive charge, one is neutral. So definitely the nucleus itself, since it has positive and neutral, it will be positive. So the nucleus is positive, the electron is negative, the atom is neutral because you combine positive and negative together eventually in the whole picture. But if you just consider only the nucleus, it is positive because what is there? Proton and neutron. What is proton? Positively charged. What is neutron? Neutral. If you combine positive with neutral, you get positive. So the nucleus is positive. If you are trying to fuse two nucleus, you are bringing positive and positive. And if you don't have high temperature to break repulsive force, because like charges repel, if you don't have sufficient heat to break that repulsive force, they will not fuse. So nuclear fission and fusion must occur at very high temperature. Now let's go to talk about the advantages of nuclear fusion over nuclear fission. What are the advantages of fusion over fission? Fusion is more easily, you can write that as nuclear fusion. Let me write this info. Nuclear fusion is more easily achieved with lightest element, e.g., hydrogen. The raw materials required from fusion are more readily and cheaply available. The raw materials required from fusion are more readily and cheaply available. Fusion process produces less dangerous byproducts. Fusion process produces less dangerous byproducts. So let's now talk about peaceful uses of nuclear energy. Many nuclear power plants are now being used to generate electricity. Beautiful. Several fission products obtained in nuclear reaction are used for radiotherapy. Radioisotopes from nuclear plants. And when we say nuclear plants, we're not talking about plants and animals, no. There are places where you have, nuclear devices, like all these nuclear weapons and nuclear, what I would call devices now, nuclear, practically sometimes I call them weapons, I call them devices, or I call them machines, nuclear machines that are involved in this nuclear, in conducting this radioactive processes of nuclear fission, nuclear fusion. Those places are called nuclear plants, like where you call an environment where those machines are located, where those devices, where those, powerful engines, nuclear engines, call them nuclear plants. Radioisotopes from nuclear plants are used in agriculture as tracers and preservatives. Some space crafts for example, ships and submarines are powered by nuclear energy. So that is it. So this is what we'll round up radioactivity part 2 with before we go into some other topics. So this is it. And I will see you in my next class.